moment we are born, we cover our bodies. Clothing has been part of the human experience since the dawn of time. We use textiles for warmth, for protection, for adornment. You could say that they are the fabric of society.
We think the first textiles were either linen or wool. People were taking wool from animals and creating fibers out of it and weaving it into textiles. Linen is made from flax, and it's a much, I won't say older product, but its use is much older than that of cotton in the Western world. Flax is harvested, beaten, and it's fibrous, and it is turned into fibers which are then woven.
We can trace linen all the way back to Egypt in the 5th millennium BCE. It was used for clothing because it kept people cool in the hot climate. Imagine wearing wool in Egypt? No thanks. Linen was also used to wrap mummies, for fishing nets, bedding, and sailcloth. Fast forward to ancient Rome.
So when we see, for example, Roman senators wearing their togas, those are actually typically made of wool. Even though they look, you see it in a movie and it looks like it's some kind of light, beautiful silk item. We do know in the ancient world as well that silks existed and cotton, but they were considered luxury items and they were typically imported from the East.
So how does a fiber from an animal or plant or even a silkworm transform from this to this to this?
So we're carding the fibers, and this process takes the cleaned, some dyed, some natural fibers, and it brings all of the individual fibers, the staple length, all into the same direction so they're getting ready to be spun. And there's a few different methods in doing this. Like I said, this is a drum carder. There are hand carders and also blending board.
But most natural fibers are fairly short. So to create a long thread, what you do is spin them together. So you would take these small fibers and you would feed them and provide a twisting motion to that through a spindle that would collect the thread and tie them all together by wrapping them around one another.
Well, I am drop spindling, which is the process of taking carded fiber and making it into a single twist of yarn. On my dominant hand, I have the distaff, which is the combed but untwisted yarn. I spread it out and then I pull with the opposite hand. Top part is called the whorl. The whorl uses centrifugal force to keep the energy for the spin, and then my pinch finger lets the energy twist up into the loose fibers and create it to twist and have yarn. This method has been used for thousands of years.
It does create more of a strength because it creates more tensile strength in the thread because they're wound together. So as you pull on it, because they're encoiled like that, you're actually tightening the thread.
Here's a fun fact. In medieval times, women who spun yarn were known as spinsters, which today has a very different meaning. They carried fiber in one hand on a distaff and a spindle in the other, using gravity to spin a yarn. How's that for a story? Later on, the spinning wheel replaced the spindle.
What's happened with using a wheel, you can move very quickly and fill up a very large bobbin. This I do today for fun. Back then, it really was a necessity. So they weren't messing around. They needed to get fibers made, yarn made, so that they could create the clothing that they would need for the winter time when the winter was coming, if they were making blankets or hats or gloves.
So this is a simple hand loom. The basic concepts are pretty much the same from the Egyptians on forward. Some of the materials in terms of, it was wool thread maybe in Northern Europe, and it was cotton or flax in Egypt. But this concept You know, all they did was incremental improvements all the way through. In fact, we still use looms and use some of the same technology names today, except it's all automated.
So now you have the threads, you're going to place them on a frame that's called a vertical loom. And it's painstaking because you have to go, and it's like a lattice work pie, to go under, over, under, over, under, over, and that's what happens with a vertical loom. In the late Middle Ages, we see there are further innovations in the loom, and that involves creating two channels.
Warping is aligning the threads front to back and creating a level base, and the weft is giving you the cross threads to bind this all together. A key thing is, as I mentioned, keeping these threads level is you got to have the right tension on this.
The innovation in the loom is the creation of additional capital. So you spend money on the loom, but you'll start making a profit because you're producing more than your own family can use. And we start to see the specialization of these guilds, where there are weavers.
And something else emerged from the ability to weave intricate patterns into cloth.
Roman women were very much involved in fashion in terms of jewelry, right? But once you start spinning metal, such as gold or silver, into very fine threads and decorating your clothing with it, which we see in the Roman times, again, we would call that fashion because in that sense it signals something. I can afford this and you cannot.
So it was all about this notion of presenting yourself through the way that you were dressed. Like linen, for example, and linen, if you read the Bible, is always associated with holy figures because it's simple and it's pure and it's woven from flax and it's usually bleached white. In the Renaissance, they were obsessed with textiles, and textiles were a way of distinguishing your class and your status in society.
We see this in your class jacket, your university jacket, where it has the name of your university on the back. That's projecting who you are. So a football player has a football jersey on, they have the knee pads, they have all sorts of textiles used for protection, but you'll see them walking away from practice and they still have them on. The difference between protection and projection is not always completely separate, in the sense that protection in, let's say, a flak jacket, right? It also projects who you are, right? So we see soldiers wearing textiles that are intended to protect them, but there is also that signal, I'm a soldier.
Today we see fashion and function blend in athletic clothing that wicks sweat away from our bodies. We wear devices that tell us how many steps we take and what our heart rate is. But what about clothing that can tell you more about your performance and overall health?
It would be great if these fibers are part of clothing and people don't know. At the moment, everybody knows they're wearing a Fitbit, everybody knows when they're holding a cell phone. The hope is that all of these functionalities are invisible to their user.
So what's the physics behind that?
So optics is one of the branches of classical physics, started really from ancient times, but it really has become a centerpiece of physics with Maxwell's equation. Optics today deals with the production of light, the detection of light, the delivery of light, and the physics advances in our understanding of optics in the 20th century have led to the internet, to telecommunication, to lasers. So optical fibers are, think of it as a pipe that guides light from one point to the other. The advantage is that optical fibers can guide light for hundreds of kilometers. In fact, optical fibers are laid down in the ground and span the globe many times over. So every 2 points on the Earth can ultimately be connected through an optical fiber. The ones laid in the ground are typically only one kind. These are fibers made out of silica glass. It's the purest optical material in existence. Imagine a glass window 100 kilometers thick, and you can see through it. That's how pure these materials are. Silica, like I said, is a fantastic optical material, so it can deliver light with the highest efficiency known in the world, but it's an insulating material. So it's very boring from the perspective of electronics. It can deliver optical functionality, but not electronic functionality. So if you want a semiconductor device to take, or an active device that take the form of a fiber such that it could enter into clothing, you need somehow to include the semiconductor in there.
So all of the action depends on what materials you put into the preform. A rod like this, you can drill a hole in that and then stack fibers that you've already made previously into this one. So now it can have 10 cores, 100 cores. We've made fibers with as much as about 1 million cores. Now each one of those cores at that size are 20 nanometers, which is 1,000 times thinner than the width of your hair.
You would take that preform and in a fiber draw tower, heat it and pull it into a fiber.
So now it's heating up, so I've set all the temperatures. The preform will slowly heat up and then soften. This should take 20-30 minutes to heat up. Right now, the bottom end of the preform is coming out. It's been heated to a point where it's soft enough to draw, to be able to be pulled, sort of like silly putty or Play-Doh. We're getting continuous information about the diameter of the fiber in the X dimension, the Y dimension, and then the average.
Some of the functionalities are, as I said, optical detection. The fiber could detect light incident on it. Another one is thermal detection. One could have a semiconductor in the core whose conductivity is a function of the temperature of the environment. So then by mapping out the conductivity of the fibers, one obtains a thermal map of the environment or of the human body if the fibers are in the immediate vicinity of the body. The fibers can emit sound or detect sound through a piezoelectric effect. So any electronic functionality could be realized in a fiber as such.
So this is a fiber where the core material has been doped with iron oxide nanocrystals. Those nanocrystals are about 5 nanometers in diameter, which, just to give you kind of a sense of proportion, that would be on the order of about 50 or 100 atoms across. By putting them in the polymer, we can now actually make fibers that have magnetic properties.
We would like, first of all, medical applications, so these fibers in a fabric would allow us to maintain continuous monitoring of the vital health signs, pulse rates, pressure, and temperature, to have a continuous monitoring of the health of the body. This will be useful for soldiers, so that if a soldier is harmed in the battlefield and is incapacitated, the clothing can maintain, his own clothing can maintain continuous monitoring and communicate to a centralized location the status of the soldier. It will also protect soldiers from, for example, sniper gun.
If you have a scope, they have an infrared laser on you to aim you up. You can't see that light because it's not visible, but your vest might be able to detect it.
That generates electrical charges that are then conducted to the periphery of the fiber and delivered to electrical circuit that issues a warning. We're also interested, like I said, in curtains, in tents, specifically for harvesting solar energy. So we'd like to make tents or curtains that collect sunlight and deliver energy. So it won't be just to protect us from the environment, but actually to collect or harvest energy from the environment. This is a $317 million project that the government is helping us set up, with the idea of building an institute that is currently known with the acronym AFOA. The aim of this institute is to transition these new technological ideas into the consumer market over the course of the next 5 years. At the beginning of the 20th century, the US was one of the biggest producers of textiles in the world. And now it's no longer the case, and there's very little amount of textile produced every year in the US. Most of these jobs have moved away. And they're not coming back because these are low-paying jobs. And the idea is, can we establish a new industry based on these new type of fibers that the US will at least have a jump start in and a lead for the next decade. So that would be one of the core missions for job development in this institute. We have the internet, and at the moment we have an emerging thing called the Internet of Things. Can we create an Internet of Fabrics? Will our clothes all be communicating with each other and with central locations, transferring information, collecting information without us knowing in a seamless way? That is also part of the mission of our institute, is to establish an Internet of Fabrics.
But wouldn't it be just great if we could create a new skin, something like that would protect us from biological threats? So I could see that as one of those innovations, but I think that might take a while. And then the last thing, of course, because this is everybody's fantasy, is the invisible suit. Put it on and you're invisible. Apparently that's a question of little reflecting mirrors, etc. Apparently it's not impossible, it's just why would you do that? Well, there might be reasons to be invisible.
Whoa. Well, that needs a little work. So, while the materials and techniques for creating them have changed, textiles will continue to serve the purpose of protecting us from cold, heat, or harm, and showing the world